UNIGINE's integrated C# component system provides a convenient programming workflow for implementing application logic via components, C# assets that can be assigned to objects, giving them additional functionality. This approach requires coding, therefore we recommend first to get familiar with programming in C# or other similar languages. The basic workflow includes the following steps. Decompose your application's logic to atomic units, components, decide on their behavior and required properties, create assets for components via the editor, implement component logic by using an IDE or a text editor, assign components to nodes in the scene. After that, you can run your application and check the result by simply clicking the Run button. By combining small and simple components, you can create a very sophisticated logic system. The component system is based on .NET Core 2.2. That's why before you start coding, make sure you've installed an appropriate SDK version that fits your IDE. You can find direct links in documentation. If this is your first time with UNIGINE, when installing UNIGINE SDK browser, you'll be suggested to install the required software, including the recommended IDE Visual Studio Code. As soon as you're ready, create a new project based on the C# .NET Core API. You'll see that component system is available by default. As the project is created, click Edit Content to run the editor. We'll check how the system works on a simple game example. Here we have already prepared some environment and content for the project. Check our video tutorials for beginners to learn basics of importing and setting up models. Every project based on the .NET Core API necessarily has the C# components property, which is the base property for all C# components. A new component is created via the Asset Browser Create menu. Specify a name and click OK. Avoid using names of UNIGINE API classes, as this may lead to ambiguity and inconvenience in coding. The new spinner component appears in the properties hierarchy. Double-click the asset to open its source code in the preferred IDE. If you use VS Code, make sure that the C# extension powered by OmniSharp is installed. A component is a C# class derived from the base component class, either directly or via another component class. Thus, you can engage inheritance of object-oriented programming approach and create a hierarchy of components. By using the component attribute containing the globally unique identifier of a property, the component is registered in the system, so do not change it. Logic of components is implemented via a set of methods called at the corresponding stages of component's lifecycle, when the component and the node it is assigned to are enabled. Initialization of all necessary resources. Update logic to be performed every frame. Resource cleanup to be performed on component shutdown, when a component or a node to which it is assigned are deleted, etc. You can also define custom methods for each stage, like this custom update method. Simply add the method update attribute indicating that this method should be executed every frame. As an example, this can be used to print debug data to the console log. The execution order of methods, either inside a single component or globally between several components, is defined by the order attribute parameter from the lowest value to the highest one. Use the method attribute for a non-custom main method to set the order value for it. Now the myUpdate method will run before the update method. Components methods are not executed when the component itself or its node are disabled. However, you can use the invokeDisabled parameter to execute the method regardless of the component state. The component class has a set of callbacks fired when a component is enabled, disabled, or ready for initialization. Override them to implement additional logic to be performed on these events. Let's apply a simple rotation. We need a rotation speed for that. In the update method performed every frame, get the node this component is assigned to and rotate it along the z-axis. To ensure stability regardless of the frame rate, the rotation speed is multiplied by the frame duration. That we get from the game class. Return to the editor, where the modified source code is processed on the fly, and the spinner component is updated. Check the console window to make sure that the component class contains no mistakes. To assign a component to a node, simply drag it to the desired node in the scene viewport. or in the world hierarchy. Another way is to use the parameters window. Add new property in the node properties section and specify the component asset right in the input field. All public fields of supported types added to the component are available for adjustment in the editor. The name of the variable defines the widget's title. Save the changes and click the Run button on the toolbar to launch the application and check if your logic works as it should. Here's the result. Both nodes are rotating according to the rotation speed value. There is a set of launch presets next to the Run button. You can extend it with your own ones by adding any of the available settings, engine configuration, graphics API, and others, including additional startup command line arguments. Once you close the pop-up with modified settings, a new preset will appear in the list, with a corresponding launch asset in the project's data root. You can rename it to change the preset name. The list of supported component parameter types available for adjustment via the editor includes basic types, Boolean, float, integer, double, and string, complex data types like arrays and lists, enumerations, structures, and even lists of structures, UNIGINE's built-in data types such as vectors, materials, properties, or nodes. By default, only public fields are shown in the editor, while private and protected ones are hidden. Using the Show in Editor attribute, you can make such fields available for adjustment, or you can hide public fields using the Hide in Editor attribute. The base parameter attribute provides widget settings. You can redefine the title of the widget, its tooltip, and the group the widget belongs to. A set of parameter attributes provides a rich variety of widgets to be used for adjustment, such as slider, mask, switch, color picker, file, material, or property, each of them with a set of configurable options. Now let's learn how to spawn new objects at runtime. Let's create a bullet, which is going to be used as a template for new nodes. Create a projectile component to implement bullet's logic. Assign it to the bullet and dive into the source code. First, we define movement speed. 5 units per second is enough, and a flag indicating a hit. We can move the bullet every frame in the update method, but considering the fact that lots of similar bullets are to be spawned, it would be better to use multi-threading here to improve performance. So let's do this inside the synchronous update method. Find the direction vector of the node in the world coordinates by providing the forward y-axis, and then just add it to the current position. The direction vector is normalized, so we can multiply it by the move speed and frame duration value. Let's also use intersections to prevent bullets from going through objects. We prepare a list to store nodes hit by the bullet and check for intersections via the world getIntersection method. This method looks for nodes of the specified type, in our case mesh static intersecting with the bullet's bounding box, and puts them to the intersected list. If there was an intersection, the list contains anything except for the bullet itself. We signalize a hit and safely destroy the bullet node in the update. Let's check our bullet's behavior. Looks all right. Now we can add visual effects for spawn and hit events to improve the look of our bullet. We'll use node assets representing these effects, combining particles and light sources. On initialization, we create a spawn effect. If the bullet spawn asset is specified, we load the corresponding node using the path to it and place it at the position of the bullet's node. Next, we do the same for the hit effect. Now in the editor, we need to specify node assets prepared for the effects by dragging them to the corresponding fields and check them. Everything works fine, but the nodes that we've spawned for special effects were not deleted. Look, the bullet spawn and bullet hit nodes are still on the scene. Not good. Without the component system, we would have to keep lists for these nodes and check their lifetime in a cycle. Not so fast, and the code becomes pretty complicated. The component system simplifies logic implementation, as the source code implementing a certain functionality is kept as a separate block written once, enabling you to combine such blocks to build a very sophisticated system. Let's create a lifetime controller containing a public lifetime and a private starting time parameters. On initialization, we set start time to the current game time, and then in the update, we check node's lifetime and delete it when it's exceeded. After that, we simply add the lifetime controller to our nodes by calling the generic add component method of the component system and set the desired lifetime for them. Note that all component-related methods are available from the component class as well, so you may drop the component system reference here. Another way to add components is to use the add component method of the node class. Let's make the bullet hit node disappear a bit faster. The projectile component is ready, so let's make our spinner spawn bullets. We'll need a reference to the bullet node, list of spawn points, spawn period, and an auxiliary timer. We initialize the timer with the delay value, then decrease it by the duration of the previous frame. When the timer runs out, we reset it and spawn a bullet at each point. This time we're going to use another way of adding a node, cloning an existing one. Since a spawn point defines position and direction for a new bullet, let's copy its world transform. We also need to enable a new cloned bullet, as the original will be used only as a template and thus disabled by default. Now we set the bullet node by simply dragging it to the corresponding field. This node is just a template, so it shouldn't be seen. Let's disable it. Each spinner should have spawn points defined. Look at these 4 dummy nodes for the omnidirectional turret. Let's create a couple more for the second turret. Next, we should add them to a list of spawn points for the respective spinner component. We define the number of points and drag them to the corresponding fields, and do the same for the other turret. You can use the right-click context menu to manage list items, rearrange, add new item, or remove an existing one. Let's check it out. We can see explosion effects, but bullets are destroyed instantly. Seems like a mistake in logic. Well, the cause is in the intersection detection. Each bullet is destroyed right after spawning as it intersects with the turret. We can simply filter out turrets and bullets from the list of intersected nodes to ignore intersections with them. For example, we can use the remove all function, excluding all items meeting the condition. Node name contains the word turret or bullet. This approach is just an example, as it's not the most efficient. In real cases, it's recommended to use bit masking for filtering. Now we should change 1 to 0, since the bullet itself is now filtered out too. And everything works fine as expected. Now we can build a playground by simply cloning the turrets in the editor. All references to nodes are automatically replaced with respective copies having necessary components assigned, without any additional coding required. The last thing left is the main player. Let's add a model for it and place it in the world. Our player requires its own component. Let's call it Robo and assign it to the node. We're going to use keyboard control, and we add move and turn speed values. Let's also add a number of health points and an explosion effect when the health runs out. Let's implement a couple of simple functions for movement and rotation. In the update, we're going to check if a control key was pressed using the input class and its isKeyPressed method. Up and down arrow keys are for movement. Left and right for rotation. Our player also needs a public method handling a hit by a bullet. Here we decrease health by the damage value and destroy the player when there's no health left. We define logic for the explosion effect separately in the shutdown method, which is called right before the node and component destruction. As we did before, we place the deathFX node at player's position and set the desired lifetime for the effect. Well, our bullets should know about the player to affect it. We can do this by creating a reference to the robo component as a public parameter. Then we can check if the node with the robo component assigned is in the list of intersected nodes. If positive, call its hit method with some amount of damage. With this approach, we'll need to specify the component for the bullet prototype by simply dragging the node and selecting the robo component. This is how you can create references to certain component in your project, but in this case, each spawned bullet will contain a link to the player node. There may be a lot of bullets during the game. Let's use another way. The player can appear in the list of intersected nodes, so we simply check each item in the list for having a robo component. You can get any component of a node by calling the getComponent method specifying the component type. This method returns the first component of the given type assigned to the node, if any. So if the robo component exists, the node will be damaged. We're almost there. Just need to specify a node containing an explosion effect. And here is the result. Regardless of the camera used, the game turns out to be pretty challenging. The component system simplifies implementation of sophisticated logic for multiple interacting dynamic objects with complex behavior while keeping high performance. For more details on how to use components for different use cases, please check our online documentation and the C# component system sample included in the SDK.